Now, in the next few slides, we will explain why we want to perform this Fourier analysis. I'll give you this example. In this example, t, the horizontal axis is time, and I basically have recorded different kinds of signals here. This is the touch tone of a telephone. So basically, when you touch the tone, you can hear some signals. Here, in these two other portions, I whistle, like, and in the last one, I say some words like, hello, how are you? And if you can see the figure carefully, I take a yellow strip, a very small part of this signal, and I perform analysis. In this graph, this is the Fourier analysis, and you will see that there are two peaks, and these have low values. The x-axis is the frequency. The y-axis tells you the magnitude. So we throw away the phase and we don't draw the phase, and immediately it is obvious to you that there are two frequencies. So in fact, in touch tone, when you're playing with your phone, they are generating two tones per button. Right, and here, when I whistle, I am whistling at this frequency, and there are harmonics over here. So even though it looks like a sine wave, if you study it carefully, it's not. Finally, when I go and this is here, then you realize that speech is a much more complicated signal than before, these previous two. The original one is nothing but a generated signal with two frequencies. When I whistle, it has one dominant fundamental frequency and harmonics. And finally, when I go then you can see that there are many, many harmonics. Now, with Fourier analysis, you can clearly now understand that it gives you a way to visualize the original signal in the frequency domain, which tells you much more information than you have if you study it only in the time domain. What can we do? Well, we can do things like a feature generation in a touch tone by recognizing that these two frequencies at which location of frequency, we can determine whether you have pressed 1, 2, or 3. Feature generation is a very important part of digital signal processing, as well as for all machine learning for classifications of audio signal. In fact, we can also do things in which many of the previous scientists have done, have used Fourier transform for compression. What does it mean? If I want to send the whole signal across a mobile phone, and you say that I need to send every sample of the signal across time, then you are sending a lot of information across the mobile phone. But in this particular example, if I know that I am only sending two frequencies, all I need to do is to send you to say that at this frequency there's this amplitude, at this frequency there's this amplitude, nowhere else. Then I'm sending you very little information for the signal of interest, and we can therefore do compression. Finally, sometimes you're interested that there are noise, and then you can use Fourier analysis to say that, okay, there's a noise component here, let's remove it. Another big use of Fourier analysis, Fourier transform, is for something called an LTI system. The word LTI stands for a linear time invariant system. A linear time invariant system is like a box in which it behaves linearly and it is time invariant. What do I mean? Let us look at this blue box, and now I have given to you a blue box, and I tell you that it's linear and time invariant. Here, this is a continuous time system. For example, when I send an input into a system, I want to see the output. In another course, you will realize that I can calculate the output simply using this equation. H of t, which is the impulse response of this linear time invariant system, and this star here is a convolution operation with x of t. This equation, y of t equals to h of t convolved with x of t, tells you how to calculate the output given the input as well as the impulse response using the convolution equation. The convolution equation is an expensive operation. It is close to n square operation, and therefore we normally do not like to perform convolution in time. Fourier transform allow us to optimize, or should I say, to make this operation much cheaper. What do I mean? Well, let us study an example, or let us just digress, for example. And when we say y is equals to 218 multiplied by 3, 4, 5, 6, 1, 2, 4, 6. And this is an expensive operation, and if you have to do it, because to multiply so many numbers together, you have to do quite a lot of adding and shifting. Now, instead, you could have done it this way. You take the log of this value and the log of this value, and then what do we have? The multiply operation become addition, and addition is very cheap. Now, therefore, we get the log of y. Okay? So, in the old days, when we want to do multiplication and we did not have the calculator, we took log, and there was using the slide rule to generate the log, and then we add things up, and then we do the anti-log. So, in the old days, we know that numbers in certain domains are easier to manipulate, and for multiplication, it is easier to manipulate in the log domain because multiplication becomes addition. What about DSP? We know that convolution in time becomes multiplication in the frequency domain. And therefore, we are interested to do things in the frequency domain. What do? We take the continuous time Fourier transform, which is nothing but analysis, which is the Fourier analysis of x of t, to the frequency domain representation, breaking down into xj omega, showing us the magnitude and the phase of the cosine wave at all frequencies. We also similarly take the Fourier transform of the impulse response, and the Fourier transform of the impulse response becomes h of t becomes h of j omega, and with these two equations, one representing the input in the frequency domain, one representing the impulse response in the frequency domain, when we multiply together, we get the output yj omega in the frequency domain. If we prefer things in the time domain, we simply perform the inverse continuous time Fourier transform, which is what it is the synthesis equation does. And then we get it in time. The operations here is simply, for example, if there's n numbers here, is n multiplication. Then you must be wondering how expensive it is to do the Fourier transform. Fortunately for us, we have something now called the fast Fourier transform, and the operation of ht to perform Fourier transform is simply n log n. So we have n log n operations to convert here, we have n log n to convert here, so we have 2n log n plus n multiplication, and this is much, much cheaper than this convolution equation here, which is an n square operation. So with that, I guess maybe the last thing which I want to talk about is something called the frequency response. In the frequency response, what is hj omega? Well, we know h of t is the impulse response. Let us recap what is the impulse response. We have a system, and we first must make sure that it is LTI, and the word L stands for linear, and TI stands for time invariant. And by linear, it means that a system will be like this. Y equals to f of x, for example. And if I have y1 equals f of x, y2 equals to f of w. And then what about f of x plus w? This will be equals to f of x plus f of w. Okay? Linear means I can break my original signal into its subparts, find the output, and then sum it. All right. Time invariant means it doesn't matter whether I do it now or I do it later. Given the same input, the output will be the same. All right. So if I have a time invariant system, the most important signal that I can send to the system is this, the impulse. If I can send an impulse to such a system, and then this system generates some impulse response, then we can use h of t for many purposes. This is the input to the system. This input is the impulse. The output is called the impulse response because the input is the impulse. It will be some function of time. Of course, it can go below as well. And once we have captured this, we can do many things. And one of the things we can do is to perform Fourier transform of h of t. And we get h of j omega. And this guy is nothing but the Fourier transform of the impulse response. And he has a name, and his name is called the frequency response. And he will be able to tell us how the system, the LTI, will respond in the frequency domain. Explicitly, what does the frequency response of a system means? It means that if I send a single cosine wave into the system, a single pure cosine wave into the system with amplitude A and frequency omega 1. Big omega 1 means 2 pi f1. Then the output of the system, interestingly, if the system is linear and time invariant, will only be the cosine wave with amplitude change by a gain as well as the phase. So this is the important information. In an LTI system, it is very interesting. When you send a cosine wave into an LTI system, out comes the same cosine wave at the same frequency with two modifications. The amplitude may change as well as the phase. Nothing else is created. So only one cosine wave went in, one cosine wave came out. The gain and the phase can be found by the frequency response of the LTI system. The frequency response is hj omega. It is the Fourier transform of the impulse response. The frequency response is a complex number. We have to find the magnitude, the amplitude, as well as the phase. So with that, please go through what does a frequency domain representation means. Remember, in our previous lecture, we showed that the Fourier transform will show the original signal, magnitude, and phase at different frequency. If this signal, the green line, is now the impulse response, when we can read off at whichever frequency of interest, the magnitude and the phase, this is the value we're interested in that will modify the cosine wave when it is sent in. And the reason why, please read this. Complex exponentials are eigenfunctions. Eigenfunctions are functions that when it is sent into a system, the function does not change except its magnitude and its phase.